Okay, guys, in P1, first thing we're going to kind of review are number systems. All these words should look familiar to you, but can you tell me what they mean? If I had to guess, probably not necessarily in all of them. What would you say about a real number? What'd you say?
No, those are natural.
Okay. If a number's not real, what is it? What would be the opposite of real? I'm not sure if you'd use the word opposite, but
Imaginary.
imaginary, right? We learned imaginary numbers last year, right? So real numbers are, there's probably no one wants to say anything that's not imaginary, okay? For a definition here, I have any number that can be written as a decimal. And I'm also going to say real numbers are all of these, okay? All of these topics we're getting ready to talk about are real numbers. So you can kind of write the definition you want. I'm going to say any number that can be written as a decimal. And I think I'm going to put in here at the end everything below. Because I want you to realize as we go through and review these definitions, rational, irrational, integer, natural, whole, these all fall under the umbrella of real numbers. Okay? What about rational number? What's rational numbers? What can they be expressed as? Nothing?
Integer.
A fraction? Now, and rational numbers are going to include integers. Okay, integers fall under that rational number umbrella here. But rational numbers, I always say it's a number that can be expressed as a fraction. If you look in the book, it'll probably say any number that can be expressed as a ratio of two numbers. A ratio being a fraction, essentially. Okay? So I'm going to say a number that can be expressed as a, and I'm going to put fraction in parentheses here, but I'm also going to try and be kind of official and say ratio. And so such as A over B, where B cannot equal 0. And that's just because the denominator in a fraction cannot be 0, right? So any number that can be expressed as a fraction or a ratio, such as A over B. Okay. Integers. What are integers? Are we getting more into the words that we remember now? It's been a long summer, huh? Or a very quick summer, but what are integers? And what I'll say is these are, you may be thinking, I've seen them, I don't really remember what they are, but these are words we need to be familiar with because they'll pop up within directions and problems and stuff. So we need to realize what an integer is when the directions ask us to use integers. Any guesses? I'm going to tell you, I'm not going to put it into words. I'm just going to put a list of examples here. I'm going to use that fun squiggly brace that everyone loves writing. What kind of numbers are integers? I'm just going to make a list of them. negatives, positives. Be more specific.
Decimals.
Can I list all my decimals though? No. So if we're not talking decimals, it's negative and positive whole numbers. Okay. So I'm going to say kind of a ... -3, -2, -1, 0, 1, 2, 3, ... Does that give you a good enough idea of what it is, includes? So integers, if I put it into words, this is not a very official definition, but I would say any positive or negative whole number. Now, the problem with that definition is you have to know what a whole number is, which I think you guys have the idea, but so integers are any positive or negative whole number. Okay, or whole numbers and their negative counterparts. Now, what are natural numbers?
Whole numbers above 0.
Okay, whole numbers above 0. Are we including 0? I'm not sure by your definition if you're including 0 or not, so I have to ask. No. When we talk about natural numbers, another name for natural numbers that you will often hear are the counting numbers. When you were a kindergartner, how did you count? Did you start with 0? Do you even start with 0 now? Probably not. As soon as I say that you don't, someone's going to get smart aleck with me and start counting at 0. But generally speaking, we don't start at 0, do we? Okay. So your natural numbers, another name for them is the counting numbers, 1, 2, 3, 4, 5, so on and so forth. What about whole numbers? What do you think of when I say whole numbers?
Not fractions.
Not fractions,
Decimals.
not decimals. Looking a lot like our natural numbers, except there's got to be a difference, so we wouldn't have another name for it.
Includes 0.
Yeah, includes 0. So whole numbers, the only difference is it starts at 0. So 0, 1, 2, 3, 4, 5, however many examples you want to put up there. Okay. And irrational numbers. We already talked about rational numbers. What are irrational numbers? We could talk about the fact that rational numbers were any number that can be expressed as a fraction. What could you say about irrational possibly then?
Can't be expressed as a fraction.
Can't be expressed as a fraction? Okay. And that's one of the definitions that I use. It's not necessarily the one I write. It's not the one you'd necessarily see in a book. Well, I don't know if you'd see that or not, but they are numbers that cannot be expressed as fractions. What kind of numbers cannot be expressed as fractions? Certain what?
Repeating decimals.
Technically, repeating decimals can. And I'll say the fraction 1/3. What is 1/3 as a decimal?
Yeah.
It's 0.333333, isn't it? And I just threw that one out because that's the one you guys are most likely to know. When I say a 1/3, that's 0.3 repeating. But they are decimals that can't be repeating. So they are ones that do not repeat and do not, what else? If I can't put it into a fraction, they don't repeat and they don't, well, I can't put them into a fraction, so we can't even talk division. They're just not going to end. Okay, if I give you some big, long, messy decimal, they're going to not repeat and not end. So decimals that do not end and do not repeat. Probably not the best shirt to wear on my first day back using the BenQ. Okay, so decimals that do not end and do not repeat. What are examples of these? Pi. Okay, pi is an irrational number, right? What's another type of number that's irrational? There's one specific type of number that I always think of when I think of irrational. I think of pi, and then I think of what could give you big, long, messy decimals if you put them in on your calculator.
I got the last root. Square root.
Square root. So, any old square root?
Huh?
Any old square root?
The not perfect square.
Not perfect squares, right? Because if I say square root of, say, 25, square root of 25 is 5, and what do we know about 5? 5 can be made a fraction, right? 5 over 1. So we need our not perfect squares. So for instance, what about 3? What's the square root of 3? Don't tell me 1.5. That's half of 3. That's not the square root of 3. Okay? Square root of 3 is one of those you need the calculator for, right? 1.7 something or other. No? Yeah, I think so. Okay, so square root of 3. I could say square root of 13. Anything that's not a perfect square could fall into this category. Okay? So those are words you need to be familiar with. Okay? Not that we do anything with them, really. You just need to be familiar with them. Okay, let's talk about our types of decimals. What are terminating decimals? Decimals that what? What's it mean to terminate? They don't repeat and they don't, or no, they do end, right? If something's terminated, it's ended, right? So anytime I think terminate, I start thinking Terminator movies, and you know. But so terminating decimals are decimals that end. Give me an example.
1.
What?
1.
1/4. Why 1/4? Yeah, what is 1/4?
0.25.
Yeah, if we divide that out, that is 0.25, right? So that's an example of a terminating decimal. And I didn't write it, but if you want to write it in here, it's a decimal that ends. As opposed to decimals that repeat. Give me a repeating decimal. Huh? No. Pi doesn't repeat.
1/3.
Okay, 1/3 repeats, yes. If you do 1 divided by 3 on your calculator, you're going to have 0.33333333, right? Or in other words, 0.3 with repeating bar. Okay, so denominators of thirds, they tend to repeat. Denominators of ninths tends to repeat. Denominators of 11 tend to repeat. Anyone happen to know 4/11ths? Is that one we know? Probably not. What is 4/11ths? See a few calculators out. What is 4/11ths as a decimal? 0. What? 36, 36, 36, so on and so forth. Or in other words, 0.36 with repeating bar over the 36. Okay, we're going to talk here a little bit about kind of knowing the difference between repeating and terminating decimals here in a moment, but we'll get to that. And I guess you kind of might want to have a calculator at your seat when we do that. But before we get to there, we're going to talk a little bit of vocabulary, and we're going to talk about interval notation. Now, remind me, did I teach interval notation in Algebra 2 last year? Parentheses, brackets, infinities, it did come up, didn't it? Okay, because that's something I'm not sure I've always taught in Algebra 2, but I have taught it some. So interval notation, I just want to kind of talk about some of the different definitions, closed, open, bounded, unbounded, those type of things. So a little bit of connection here. Oh gosh. Okay, so here is an interval that goes from point A to point B. Okay, so a little bit of notation to help us pull this together. How can I write this, express this interval in terms of inequality symbols? So before we get to our interval notation, think inequalities. So less than, greater than type symbols, yes? So what is shaded here? The area where? Between A and B is shaded. Do you remember how to write that as an inequality?
A is greater than or equal to?
No.
All right. Less than or equal to?
Uh-huh. I wrote the X without thinking, and then...
Less than or equal to B.
Yeah. Because the shaded part's in the middle, yes? Now, if we reverse this, and this may be what Stetson was doing here, it's shaded greater than A, isn't it?
Yeah.
So if you're just thinking about that, that is shaded. I mean, you can think of it as, okay, this is X greater than or equal to B, and X... Wait, I said that wrong. Greater than or equal to A, less than or equal to B. But we combine them into one. It reads A, less than or equal to X, less than or equal to B, yes? And those signs will always be going the same way. Now, that's with inequalities. What if it's interval notation? Well, first of all, if we're shading on the line, what do we have instead of those endpoints? Like if we're shading on a line, like, you know, think about this line being going farther. But what do we do at A and B?
Oh, arrows. Like floating arrows.
Not, no, don't think arrows. Think,
I don't think we did that.
we didn't do brackets?
No.
No.
We did the open circles and closed circles.
Okay. We did endpoints with circles, but we didn't do the endpoints with brackets and parentheses, you don't think?
No.
Okay, and that's possible. This is one of those, I teach Algebra 2, I teach pre-calc, where does it come in? I kind of thought I introduced it in Algebra 2 last year. I don't know, we'll see when we get to the next page and we do some examples. It will be apparent then whether it is old news or new news. Okay, so if we have an interval notation, that's fine, because I often introduce it right here. So you guys are probably used to seeing the endpoints. Okay. We also will sometimes use, instead of endpoints, and keep in mind this line could be extending past here, but brackets. Now notice those are square brackets, right? Not drawn very well by me, but those are square brackets. If we are expressing this in interval notation, my shading goes from A to B, and we use brackets on either end. Okay? And those are closed intervals. Now, what do I mean by open intervals?
Like the open circle.
Okay, exactly. When we talk about, and I'm going to use A and B again, but instead of, when we go back to what you've been doing for years, you have the open circles representing your points, right? That's an open interval. Instead of A less than or equal to X less than or equal to B, what changes?
Is greater than or equal to. Or no.
No?
They're not equal to. They're just.
Yeah.
Oh yeah.
And when less than or equal to and greater than or equal to were said earlier, I didn't ask why are we putting an equal to on there. I should have. But why did we put equal to on these signs earlier? Because the dots were filled in. Why am I not putting equal to now? Because the dots are not filled in. So this is A less than X less than B. Okay? Now, what's it change up when we start talking about interval notation? So like this is inequalities down here. Interval notation, instead of square brackets, we use parentheses. And again, I'll show you some examples on the next page. When we write interval notation here, it's still the interval is shaded from A to B. But if they are not equal to, they are open values, then we use parentheses instead of these square brackets. Okay? A little bit of vocabulary here. What are the endpoints I just used in those two examples? A and B, right? So endpoints are just your points at the end. I don't really need to say much there. Okay, bounded intervals. Bounded is a word we talk about in pre-calc. We'll talk about when we get to chapter 1 as well. But if something is bounded, it has boundaries. It has endpoints. Okay? So up above, we talked about closed and open intervals, right? Those fall into the category of bounded intervals. So any closed or open intervals, like what we did up above, those are bounded, okay? Because they have boundaries, they have endpoints. So I'm going to say any close or open intervals, I'm going to say such as above. Now, unbounded. Okay, something's bounded, it has endpoints on both ends. Yes? If something's unbounded, at least one end does not have an endpoint. So this is a situation you're going to think like X is greater than A, or just X is less than B. Okay? You're not going to have endpoints on either end. One end is going to go infinitely. Now, with that in mind, try to decide how I want to do this. Normally you use arrows, right? We'll use arrows to show our shading or whatever. But we're going to use, in our interval notation, we're going to use positive infinity, which will be represented if something is increasing to the right. Or I'm going to use negative infinity. And that would be if something is decreasing to the left. And I will set up a set of examples here. So, if this is, I'm going to change this dot here in a moment. I'm going to take the dot off here in a moment and put something else. But what would you say this is if you're trying to describe this as an inequality?
A is
Greater than or
equal to negative infinity.
Well, okay, not what I was going with there.
Or like A and then comma negative infinity, but A would have the bracket and then B the little parentheses.
There, you're getting there. What I was going with, okay, so I was just thinking back to inequalities. And I was just thinking about like this would be, could you agree that this would be X is less than or equal to A? If we go back to inequalities, yes? Putting your X first, your A, and then where is the shading in relation to A? It is to the left. It is less than, right? So X is less than or equal to A. Now, if we talk about this, that is a closed circle, so I'm going to replace this with a bracket. If we talk about this as a bracket, think about your shading. Where does my shading start? Well, my shading starts technically what? Over in Mr. Stanley's room, Mr. Summers' room, Mrs. Holman's room. It starts way over there, doesn't it? Okay. What do we represent that shading then? Where does this interval start? It's starting down at, I think Katie just said this, negative infinity, yes? So the idea here is if you think about, okay, it starts at negative infinity, Where does my shading end? At point A. Now, A is going to have on it a bracket because it was a closed endpoint. Infinities always use parentheses, no matter what. Okay? Or, let me show you the other option here. Here's my B. Now, if we see this and we're asked to write an inequality, what is this as an inequality? This is X is what? Where's my shading? Yeah, it's going to the right of B. It's greater than B. Notice I didn't say greater than or equal to, did I? I just said greater than. Well, what's that look like? As interval notation. Now, keep in mind, instead of an open circle, what would this be? It's now a parenthesis. And so look at this interval. This interval goes where? It starts at B. And where does it go? It goes off to Miss Minnick's room, which is positive infinity. Now, in this case, the B had an open interval, so we're going to use a parenthesis. And infinities always use parentheses. Okay. These would be more unbounded intervals. Okay, these are unbounded because they go infinitely one way or another, or maybe both ways, who knows? Okay, but these are examples of unbounded intervals. When we get to the top of the next page, we're going to practice going back and forth between inequalities and interval notation. Because interval notation is something you have to understand. When we get into chapter 1, we'll be using interval notation more than inequalities. Interval notation is a expected necessity in calculus, so we have to kind of get it pretty set so we know what we're doing. Okay? Okay. Let's go look at some exampple here. Determine if the following decimals repeat or terminate after finding the decimal form. Now, we can do this the easy way, we can do this the difficult way. I don't know about you guys, but I'm not opposed to the easy way to an extent. Okay? So if you have your calculator and you want to grab it out, you can. What do you know about 1/16? And maybe you know this without calculating this one. What do you know?
It terminates.
It terminates? Okay. And this is one that, while some days I might not be able to give you the exact decimal, I can tell you 1/16 that terminates. Okay. So this is going to terminate. What is this decimal?
0.0625.
Now, if, I don't know, I felt in a torturous mood, how would we do that without a calculator? How would we get to that 0.0625 without a calculator? You divide, right? If I force you to for some reason, I'm not, so don't worry. It'd be 1 divided by 16, wouldn't it? Okay, so just kind of as a friendly reminder, if you had to for some reason, it'd be 1 divided by 16. Okay, what do you know about 55/27?
It repeats.
It repeats? How can you tell it repeats?
It's 037, 037.
Okay. And what, does it end at 037 or does it?
Yeah, it stops.
Okay, so you don't have any other random numbers there? Okay. And what I will say, okay, wherever your calculator stops, depending on what digit you stop at, 037, 037, if you stop 0370, well, technically, no, I'm saying 037, and 7 is, no, okay, it'd be if you stopped at 03, like 037, 037, 037, and then 03. What technically does the 7 tell that 3 to do? If we were rounding, the 7 would tell the 3 to go up to a 4. So realize, just because on your calculator you might see a 4 thrown in at the end there, your calculator might be rounding that last digit depending on the settings, okay? But this is indeed 2.037. Would long division show us that? It would take a little bit of work, right? But doing 55 divided by 27, it would get us there. We could keep going. We could show that it repeats. What about C? What about 1/17?
Terminates.
How do you know?
Because it doesn't repeat.
Okay. Do we know that for fact?
I think.
Valid answer. So our calculators go, I don't know how many digits,
To 294 is the last.
which is 9 digits after the decimal, according to my counting there. Could it start repeating at some point after that?
Probably.
Now, you guys have sat in my classroom long enough. What am I going to say when you see something like that on the calculator? I'm going to say it probably doesn't repeat and keeps going on, doesn't it? But here's what I'm going to tell you. If we were to work this one out by hand, guess what?
Keep going.
It repeats.
Oh.
Okay? Now,
So I was lied to. Straight up, right to the
I don't know that I'd say lied to. You just don't have enough information in front of you. Now, it is still a common assumption, and I know assumptions get us into trouble. It is a common assumption to assume that if you don't see any repeating on the calculator screen, it's not going to repeat. However, this one does actually repeat. And in order to prove that, you could prove it using long division. Again, I'm not feeling that torturous today, so. When we have 0.588235294. Doesn't appear to repeat, but it does start repeating. Okay? So just kind of a calculator trick to be aware of, so to speak. Okay, ready for the next page? Okay, back of this page, we get a little bit of practice of going between inequalities, interval notation, and words. Okay, so this first set asks us to describe and graph the interval of real numbers for the inequalities. So describe and graph. So what does that read, first of all? X is less than 3. And so what does that mean? X is less than 3. I agree, that's how we read it. But that means numbers that are what? Less than 3, right? So all we could say real numbers. I think that's what I used, yeah. Real numbers less than 3. Okay, so when it asks for describe, think words. Okay, think words. Now, this also asks us to graph this. Okay, there's my help. There's an underline. What do I put on this graph to graph it?
3.
You've got to have a 3 at least, right? I'm going to say I want a few more numbers than just 3.
And then 2.
Okay, so I'm going to say 1, 2, 3, 4, 5. How do we graph this?
You put like the open circle on 3 and then go to the left of it.
Yes, but I'm going to tweak that. Instead of using the open circle,
Would it be a parenthesis?
I'm going to have us use parentheses. Now, I'm not disagreeing with open circle, yes? I'm trying to get us into this interval notation idea. And so instead of an open circle, you have a parenthesis. Because we're shading to the left, the parenthesis opens to the left. Does that make sense? And again, it's habits I need to get you guys to get into in pre-calc. This is just kind of trying to get you guys used to this. Are we good there? Okay, let's try B. What does this represent if we put it in words? Numbers that are what?
Greater than -1, but less than or equal to 4.
Okay. What does that mean they're going to be on the number line?
Between -1 and 4.
Right? So when you see something like this is saying the numbers between -1 and 4. And so I'm actually going to put this as real numbers between -1 and 4. And I'm not opposed to what Katie said at the beginning, okay? Just realize that. Now, what can we say about the endpoints, though?
-1 is a parenthesis, 4 is closed.
Okay. So we've got opposite things happening on the endpoints. So in terms of excluding or including, -1 is going to be excluded. So I'm going to say excluding -1 and including 4. And again, multiple different ways. This is something you'll have to do in homework. Those you'll be writing some stuff out. Now, number line. Well, you have to have some numbers on here, yes? Minimum, your numbers are going to have to include -1 through 4, yes? Minimum expectation there. How am I shading this?
Parenthesis from -1 to the right.
Okay.
And a close circle.
Except I'm not using a closed circle,
A bracket.
a bracket. So yes, it would be an open circle and a closed circle in any equality notation. But if we go for parentheses and brackets, it's going to be as such. Okay, guys. 10:14, right?
Yeah.
So this is a good stopping time. Although, not sure if my clock's exactly on. We're going to stop here, which means we have a couple more examples to do in this area. And we have some exponent type examples to look at. There is a third page to this set of notes. Okay, so we'll pick up there tomorrow. Bring book and or iPad. Okay, plan on some work time tomorrow. We should definitely have some. So bring your book. You want to check out Schoology, and you can even do that tonight if you want to. Try and download the book. Remember, I don't care. You can, what I told you guys Friday, for those of you that weren't here, is carry the book every day to class with you, or carry an iPad with the book downloaded on it. I don't care as long as you have access if we have work time or homework questions if you need access to the book. Okay, bring some form of the book with you.